Let's take an example of a cantilever one-dimensional bar element. So this is the problem that you're given. A thin steel plate and the thickness, the Young's modulus and the density, they're all given in terms of pounds and inches. This unit here, PSI, stands for pounds per square inch. LB stands for pounds. And in addition to these forces, you also have a concentrated force P, which acts at the center of the element. We can start by dividing this element which is given to us into two elements. So we will divide it at the point of application of the force. So this is how we are going to divide it. It's going to look like a stepped shaft after the division of the elements. So this is what we have, and this is the axis. Each plate is 12-inch long. Now we need to find out the average of these plates. So the width at the top at the fixed end is 6 inches, and it is gradually reducing to 3 inches at the bottom of the plate. If we interpolate at the center of the plate, it will be 4.5 inches. So now we want the average between these two. We have to work it out like this. So it will be 6 plus 4.5, the whole divided by 2, which is 5.25 inches. So this width of the top plate is 5.25. This is plate 1 and the second one is plate 2. So we have node 1, node 2 and node 3. So this is 5.25 inches. The second plate will have an average width of 4.5 plus 3 divided by 2, which is 3.75 inch. We need to find out A1 and A2. So A1 and A2 are the cross-sectional areas of the element 1 and 2 respectively. If this is my element 1, the thickness is given as 1 inch and the force is acting here. So the cross-sectional area is this area. A1 will be equal to 5.25 into 1, which is 5.25 inch square. Similarly, A2 will be 3.75 into 1, which is 3.75 inch square. We need to find out the element stiffness matrix. So let's start with element 1. K1 is given by A1 E1 upon L1, 1 minus 1 minus 1, 1. Substituting all these values, solving this, we get the following. Here we need the element connectivity table. So we have element and nodes 1 and 2. So for element 1, the first element is 1, first node number is 1 and the second node number is 2. Similarly, for element number 2, the first node number is 2 and the second node number is 3. This degrees of freedom we shall write here The same way we find out K2 for element 2. And on substituting all the values, we get this matrix. Again, writing the degrees of freedom, this will be 2, 3, 2, 3. Same way, we have to find out the force vectors. So for element 1, due to the self weight, rho indicates the density, putting in these values, we get and the degrees of freedom of 1 are 1, 2. For element 2, F2 will be A2 into L2 into rho 2 upon 2, 1, 1. The degrees of freedom of this are 2 and 3. So these are the body force vectors. Next, we need to assemble the global stiffness matrix. The bar element shown has 3 nodes. So the degree of freedom is 3 and the size of the stiffness matrix will be 3 by 3. So we have 1, 2, 3 and 1, 2, 3. So here we have 13.12 into 10 to the power 6 minus 13.12 into 10 to the power 6, 0. Here there will be an addition of terms. So it will be 13.12 plus 9.375 into 10 to the power 6. This is minus 9.375 into 10 to the power 6, 0, minus 9.375 into 10 to the power 6 and 9.375 into 10 to the power 6. The global load vector will be given by F and it will be of the size 3 by 1 again. Here we have node 1, node 2 and node 3. At node 2 it will be an addition of these two values plus there is a point force and all this works out to be 115.3144, so 6.381. We are asked to find out what is the displacement using the elimination approach. Okay, so we are going to write this in the form of K into Q equals to F. So let me rewrite all these terms. (13.12 into 10 to the power 6 minus 13.12 into 10 to the power 6, 0, minus 13.12 into 10 to the power 6, this is 22.495 into 10 to the power 6 minus 9.375 into 10 to the power 6. So this is the K matrix, global K matrix. The Q vector will have Q1 is the displacement at node 1, Q2 and Q3 are the displacements at node 2 and 3 respectively, and this is a global load vector which we just calculated, 115.3144 and 6.381. Now in the elimination approach, what we do is we eliminate the row and column which has no displacement. So in the problem that we are given here, we see that node 1, okay, this node 1 is fixed, so it will have no displacement. So the rows and columns corresponding to node 1 have to be eliminated. So this is row 1, this is column 1. Okay, so throughout, on the left hand side as well as on the right hand side. So now what we are left with is a 2 by 2 matrix. So there are two equations and two unknowns which can be solved, and we get the answers of Q2 as 9.27 into 10 to the power minus 6 inches and Q3 as 9.95 into 10 to the power minus 6 inches. Next we are asked to find out the stresses. So for element 1, we can write sigma equals to EB into Q. We know the value of E. B is given as 1 by L minus 1, 1. And this Q will be a matrix of Q1 and Q2. Okay, here we could write Q1 equals to 0. So Q1 is 0, this is sigma 1, and Q2 is 9.27 into 10 to the power minus 6. So substituting all these values here, we will get the value of 23.175 psi. Similarly, for sigma 2, for element 2, sigma 2, 30 into 10 to the power 6, 1 by 12, minus 1, 1, 9.27 into 10 to the power minus 6, 9.95 into 10 to the power minus 6, and the value we get is 1.7 psi. To find out the reaction at node 1, the calculation requires the first row of the K matrix, that is the 3 by 3 K matrix obtained earlier, and the externally applied load. Okay, so we need the first K matrix. We'll get the reaction as Ku or Kq minus F, that is 13.12 into Q2, the 0 into Q3 minus 8.9334, and this we get as minus 139.17 pounds. This has to be equal and opposite in direction to the applied forces. So the negative sign indicates that the reaction is opposite. So first add all the forces that you all are getting due to the applied and see if it is equal to this value 139.17. Thank you.